Welcome to the next video in the Combinatorics sequence. This video I'll be doing exercises 1.1.5 to 1.1.9. So for a first exercise, we're going to show that this expression always evaluates to an integer for every natural number n. I suggest that you pause it and come up with a solution on your own, but when you're ready, here is a first solution, but it is actually one that I don't recommend even though it works. And here's the reason. Okay, so what do? We factorize the numerator. You can figure out that this is the factorization because obviously n factors out, and then in what's left over, you can like plug in 1 and see that 1's a root, and you can do like long division, right? You can, kind of get to this point. Get this factorization, and you notice that the factorization is 5 consecutive natural numbers, or integers at least, and we want to prove that this is divisible by 120. Well, you look at the prime decomposition of 120, which is 2 to the 3 times 3 times 5. Well, certainly, right, and so we want to prove that this expression is divisible by 3 and 5 and 2 to the 3, and then it's divisible by 120. So the fact that this is divisible by 3 is kind of trivial because, after all, if you've got 5 consecutive integers, at least one of them is congruent to 0 mod 3, so it's divisible by 3. Likewise for 5. The 2 to the 3 part is a little bit harder, and really that's kind of why I think this solution method is not a good solution method, in part. I mean, actually, really, the reason why I think this is not a good solution method is because this has nothing to do with the section that we were just studying, so why is this here, right? This doesn't seem like it's exercising the thing that we were intended to exercise. But it is possible to give a proof that 8 divides this number, but you have to like go by cases, and again, right, none of this has too much to do with what the section was just talking about, so I recommend against doing it this way, even though it is possible. Now, the way that I recommend we do it is we notice that the denominator is 120, which is the same thing as 5 factorial, and that can't be an accident. How could you, right, like what kinds of things have we seen that could get you a 5 factorial in the denominator? Well, think about maybe n choose 5, right? N choose 5, if you cancel all the factors in the denominator and the numerator, or at least the ones that, can clearly be canceled, you get this expression, which again has 5 consecutive integers, and it has 5 factorial, which is to say 120 on the bottom. That's going to be an integer because it counts the number of elements in some set, right? We know that, every binomial, every value of the binomial function, n choose 5, is going to be an integer because it counts something. Has to be an integer. So that's the logic behind this solution. Now, this expression is not exactly the same as the expression that we wanted, but it is still 5 consecutive integers divided by 5 factorial, so we must be close, right? And in fact, you can just perform a transformation, like let's say call m n plus 2. It transforms the given expression into this expression that we identify as m choose 5. Now, this is valid for m greater than or equal to 5, which is the same thing as n greater than or equal to 3. So this basically constitutes the proof for when n is greater than or equal to 3. And in the remaining cases where n is between 0 and 2, well, it's easy enough to see that the expression evaluates to 0 in all of those cases and therefore is divisible by 120 trivially. I think that's perhaps, right, just sort of construing this as something to do with count. Okay, so moving on to exercise number 6, we're going to now count all possible orderings of a 52-card deck which have the spades occurring consecutively. Now, my solution is that the block of spades, right, one of the first things that we can count is where do we initiate the block of spades, we know that wherever it initiates, it then carries on for 13 cards. And so how many locations, right? If you line out the cards of the deck from first to last, then the spades could occur in the very first card, and then it must carry on for the next 13. Or it could initiate at the second card, or so on, out to the 40th card, right? So the 40th card could be a spade, and that gives you just enough space for the next 13 cards to all be spades, and then you run out of the deck at that end. So that effectively means that we have 40 choices for where we initiate the block of spades. Once we have chosen where the block of spades initiates, all that remains is to count the number of orderings inside the block and the number of orderings outside the block. So if we have the block of 13 spades, then there are 13 factorial ways to rearrange the spades inside of that block. And then outside the block are 39 cards, so there are 39 factorial ways to rearrange those cards. So at the end, the number of such decks is 40 times 13 factorial times 39 factorial. Okay, on to exercise number 7. Here we're going to compute the probability that a random set of 5 cards drawn from a 52-card deck has at least 3 cards with the same rank. So a way that we could diagram sort of what we're talking about is that we could say that we're looking for x, 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 y, z. The x's representing some rank, right? Let's just say that it's from 0 to 12, actually. There will be a reason later on why I might want to sort of enumerate it in that particular way. But, so we can identify, right, a card of rank 2, we could identify with the number 0. A card of rank 1, we can identify with the number, rank 3, we identify with 1, and so on. And so an ace would get identified with rank 12. And so these x's, right, these 3 x's represent some repeated 3 ranks, and the y is possibly some other rank, although possibly not, right, because we are saying at least 3 cards with the same rank, so that permits possibly also 4 cards of the same rank. But also y may not be the same rank, and then z is some rank also that may be different from the first other choices. So this is maybe kind of a diagram of what we are talking about when we talk about the having 3 cards of the same rank. And the only thing that is then going to distinguish these cards, because they are different cards, they must be distinguishable somehow, so they will be distinguished by the suit that they have. So in this diagram, what we could imagine is that we first have to pick the rank that is going to be repeated 3 times. So there are basically 13 different ranks to choose from, so we're going to multiply in our answer the number 13. Having chosen the rank, we next need to choose 3 suits out of the 4 available for that collection of 3. So there are 4 suits in total. We will choose 3 of them to be the suits that make up the x's. Then what you can imagine, and I should warn you now that this is a bit of a false answer, right? I'm kind of showing you an initial thought process and then how you want to sort of audit it and be careful, because these things can be subtler than you might initially imagine. But anyway, so if we imagine, then there are just some 2 remaining cards and we don't care which ones, so we will choose them, right? So if we've already taken from the deck some 3 cards, then that leaves 49 cards left to choose from, and we want to choose 2 of them. So you might imagine that this is the solution. However, if there were 4 cards all of the same rank, then we would have found a way to choose 3 of them here, and then another 4th one of the same rank in in one of these other variables like y. And the problem is that this gets us multiple countings of the same scenario. So imagine that you had 2 of spades, 3 of spades, 4 of spades as the way that you could form, 2 of spades, 2 of hearts, 2 of diamonds, or something like that, right? So that would be one way that we could have chosen 3 cards of the same rank. So I had spades, hearts, diamonds. And then maybe this y, the card that we choose for y, is the 2 of clubs. Well, that is in fact the same scenario as if the first 3 that I picked was 2 of clubs, 2 of diamonds, 2 of hearts, or something like that, and then the last one is the spades, right? So I would have counted that same scenario multiple times, and in fact, those aren't the only ways, right? There are many other ways to like rearrange the division of the 4 cards of the same rank into these different groups. So I would have multiply counted the same scenario, and this is not right. This would be an overcounting. This would get you an answer that is too large. So let's see how to do it the right way after we realize that this way of counting is too large. Probably the most obvious way to correct this is to say, okay, well, maybe I was just too ambitious in trying to count it all in one go. Let's break it into 2 subcases. One in which there are precisely 3 cards of the same rank, and the remaining 2 cards are of some other rank than the first rank that was chosen, right? So basically, precisely 3 cards of the same rank, and any other 2 cards other than that rank. Well, by that logic, we would then say, okay, still 13 ways to choose the rank that is a triple, 4 choose 3 ways of assigning them suits, but because the remaining 2 cards are required to be of different rank than the first one, although I've only chosen 3 cards, I'm in fact eliminating all 4 cards of that rank from the choice of the next 2. So now I have 48 choose 2 possibilities for the remaining cards. And that's how you count it up if there are precisely 3 cards of this shared rank. But we know that we are supposed to also allow for 4 cards of the same rank, so we count that separately. Again, right? So now we could kind of diagram that as saying, okay, so now I'm taking this diagram to be a strict diagram, strictly requiring the x's to all be the same and the y and the z to be at least distinct from x. All right, they may be right. Y and z might be equal to each other, but they're at least distinct from x. And now I'm going to count it up where I actually have 4 cards of the same rank, because the problem instructs that we are supposed to also allow for this. And then there is only 1 remaining card, which we could call y, and we want to count this up. 13 ways to choose the quadruple, and then having chosen that quadruple, there's nothing to count as far as the suits are concerned, because we just take all of the suits. There's really no option there. And then 48 cards remain for the y. So 13 times 48 would be that part. You add them together. Now you have the correct answer. Okay, so we are now going to count the set of 6 cards from a standard deck such that the hand has at least 1 of every suit. And so in this setting, it's worth thinking about the number of ways that we could apportion the 6 cards to the various suits. So, for instance, you could go 3, 1, 1, 1, right? That's 6 cards, 4 suits. It doesn't really matter which one we take to be which, but I guess, if we want to just be specific. We could say, like, that's the diamonds, that's the hearts, that's the spades, and then that's the clubs. So that diagram would correspond to the diamonds getting 3 of the cards and everything else getting 1, for instance, right? That's one way that this could go. Of course, the 3 could go actually with any suit. So we know that that's something we'll want to account for eventually. And then this is not the only way that it could go, right? I mean, obviously, we could also have 2-2 and then 1-1, right? But there are no other possibilities, right? So really, these are the only interesting possibilities. How many rearrangements are there for this 3-1-1, right? How many other ways could we have given some suit 3 and everything else 1? Well, basically, there are just 4 choices for which suit gets the 3. And in this one, how many ways are there to rearrange which suit gets the 2 cards and, so on? Well, I need to take the 4, choose 2 of them to be 2s. So 4 choose 2 rearrangements of that. And so next what we want to count is how many ways could we choose the face value? Like let's go back to this and ask, how many ways could we give the triple face values? Well, there are 13 face values and I want to choose 3 of them to go to this card. So 13 choose 3 as the number of ways of giving face values to the 3 cards of whatever suit that was. Now, what about the number of ways of assigning face values to the remaining suits? Well, okay, so 13 for the first singleton, 13 for the next one, 13 for the last one, okay? And so if the cards went this way, this counts up how many possible 6-card hands are like that. Down here, we do a similar thing. Right now that I've got 4 choose 2 ways of picking suits to be the doubles. Once they are picked, then I've got 13 choose 2 ways of giving face values to the first double, and 13 choose 2 ways of giving cards to the second double, and then 13 ways of giving cards to the first singleton, and 13 ways of giving cards face values to the other singleton. And then if you add these together, then you've got, okay, so for the next one, we want to count the integers from 0 to 99,999 such that each digit occurs at most twice. Leading zeros are counted as appearances of 0. The solution here, or at least one solution in this problem, is very similar to the previous one. We basically can, again, think of like, okay, so if I'm going to pick a double, right, I basically want to say, look, I could either have 2, right, and by the way, we basically just regard every number as 5 digits, and so we're talking about words formed from the alphabet of 0 through 9, at the digits 0 through 9, right? So these would be length 5 words formed from that alphabet. And so every number has 5 digits, and I could pick some 2 digits to be the same and another 2 digits to be the same, and that leaves just one more digit if I'm going to have length 5, which must be a singleton. On the other hand, I could have done some 2 digits the same and then 1 and then 1 and then 1. That'll still have 5 digits. Or I could do 1, 1, 1, 1, 1. That'll have 5 digits, right? And so in each of these cases, we count something up. So in this first scenario, I need to pick 2 digits to be the 2 doubles. So that is to say I've got 10 digits to choose from, pick 2 of them, And then the last one could, right, the last digit could be chosen in any of 8 ways because 2 digits have already been taken. And then having chosen what the digits are, then I just need to find all ways of rearranging them. And we can use the multinomial formula for counting distinguishable rearrangements. So maybe if this needs explanation, I can explain it in some other video. But basically, the multinomial, right, I'm going to have 5 factorial because it's a length 5 word. 2 of the characters are going to be indistinguishable, and then another 2 are going to be indistinguishable, and the last one is distinguishable from those. So anyway, so that's the multinomial function. And yeah, so I've counted up this first scenario. Now in the next scenario, I need to choose some digit to be the double. So I've got 10 choices for which one's going to be the double. And then having chosen that one, I want some 3 others to be singletons. So I've got 9 to choose from, and I'm going to choose 3 of them. And then having chosen which ones are going to be the double and the 3 singles, I need to find all ways of rearranging. Again, I'm going to use the multinomial to say 5 factorial over 2 factorial, and then everything else is a 1 factorial. So I might as well not even write it. And then here I just have 10 choose 5 ways of picking the digits, all of them distinguishable, and then 5 factorial ways of rearranging them. So in the end, and I see that this has gone off the slide, so you can't read the slide exactly, but it kind of doesn't matter because I've already done it on the screen. So hopefully, yeah, and again, it's gone off the screen, but you can see basically just by adding these things together, I get the total count. So there's the solution.